Welcome to lecture 18. We're going to be talking about cache block sizes and writes, how to handle them in caches. A couple of announcements. A couple of deadlines are coming up next week. Homework 4 is due next Tuesday. Project 3 is due next Thursday. So please get started on them if you have not already done so. We have received a number of midterm regrade requests. We are working on them. They should be resolved by this week, so please look out for an announcement. Alright, so let me spend the first part of this lecture recapping what I explained in lecture 17, where we went over memory hierarchy and a basic cache design. So here is an alternative representation for thinking about the various memory technologies. So on the x-axis you have cost represented as dollars per gigabyte, and on the y-axis you have latency or the access time. So ideally we want a memory technology that is both cheap and fast, but unfortunately we don't have any memory technology that is as good as that. Instead, what we have are expensive SRAM, which tend to be small because they're expensive. And then we talked about DRAM, which is 1 to 2 orders of magnitude cheaper but also slower than SRAM. So in 370, we primarily talk about SRAM and DRAM memory technologies. And when we talk about caches, we talk about SRAMs. We also briefly talked about storage technologies. These are non-volatile devices, meaning when you turn off the computing system, the data doesn't vanish. The conventional solution are hard disks. They're very cheap, they're very dense, but they're also really slow. The newer solution is flash. They've been around for a long time, but only recently they have gotten into laptops and mobile phones. They are much faster than hard disks, but still much slower than DRAM. The newer memory technologies like phase change memory is trying to bridge the gap between flash and DRAM, and they are faster than flash, but also cheaper than flash in some cases. So the other important concept we talked about is to organize these different types of memory technologies into a memory hierarchy or a memory pyramid. And the way we organized it is to place fast but expensive SRAM on the top of the pyramid, and slow but cheap devices like a disk at the bottom of the pyramid. And the main idea was we will exploit program locality. We talked about temporal locality in the previous lecture. So we'll exploit program locality to identify the set of addresses that I'm going to be accessing in future and store that working set of addresses in my highest level of memory hierarchy, and then store the remaining in the next levels of memory hierarchy. So here is a more concrete configuration for the different technologies used to build a modern memory system hierarchy. So you have the disk, which today can be as large as several tens of terabytes, but they're really slow like we talked about. And the top you have register file, and you have caches. Now there are three things I want to talk about this slide. The first one is you'll notice that there are 3 levels of caches as opposed to just one that we've been thinking about so far. We won't go into much detail into these 3 levels in this course, but I'll try to briefly explain why we want to have 3 levels of caches. So if you just use the first level cache, it's super fast. It's just 1 nanosecond to access the cache. It pretty much operates at the same clock period as a processor's clock period. So if you access a cache, you don't have to stall your data path. But the problem is it is very small. On the other end of the spectrum, you have main memory. It's few gigabytes in size, but it is 2 orders of magnitude slower than L1 cache. What we want to do is to bridge this gap in performance and size between L1 cache and main memory. And the way we do it in modern systems is by adding 2 more levels of caches in the hierarchy. And they vary in terms of size and latency. So L2 is much bigger than L1, but it is also several seconds slower than L1. Similarly, L3 can be a few megabytes in size, and it will also be much slower than L2. So because it might take a few tens of cycles to get the data as opposed to a few cycles. The second thing I want to talk about in this slide is the ISA abstraction. So we mentioned this briefly in the previous lecture as well, and I told you that the memory hierarchy is hidden from the programmer. What that means is the geometry of the different caches, the sizes, the size of the memory, the disk, and what data remains where. All of those details are hidden from the programmer. The programmer does not have to worry about any of that, right? So if you write a program in C, you don't think about caches, right? So as a result, the programming can be a bit easier. But we do expose the register files, which is a form of a storage, to the programmer. And so the programmer gets to see how many registers are supported by the hardware. So in LC2K, there are 8 registers, and when you write an LC2K program, you can specify what data should be stored in any of those registers. Now, if you write a program in a higher level language like C or Java, the higher level language gets compiled down to the machine language, which is like LC2K or ARM or x86, and the allocation from the programmer defined variables to the ISA defined registers is done by the compiler. If you're writing your program in assembly language like LC2K, then you as a programmer would do it manually. So this register file is really managed not by the hardware, but by either the programmer or the compiler. When I say managed, I'm talking about what data is stored at any time, and when you're running out of space, then you need to select a victim. We talked about the replacement policy in the last lecture. The victim is selected by the manager, and you bring back the data into the cache or not. All those decisions is what I mean by management. Now for registers, like I said, it is done by the programmer or the compiler, but for the caches, it is done by the hardware. The reason why programmer and compiler cannot do it is because, like I said before, caches are not exposed to them through the ISA. So it has to be done in hardware. Now if you look at main memory and swap disk, main memory sort of acts like a cache for the swap disk, right? Because it stores a subset of the data that you have in the program. Now the decision on what to store in memory, when to replace, what to replace, those decisions are made by the operating system as opposed to the hardware. And the reason for that is the frequency of data transfer between main memory and swap disk is really low. You don't really go to the disk that often, and so there is no real need to provide hardware support to handle such an infrequent operation, and that's why you delegate that functionality to the operating system. So when we talk about virtual memory later on in this course, we will revisit this issue and understand how does the operating system manage this data transfer between main memory and swap disk. So for now, we are going to remain focused on caches and think about just one level of cache for the moment, and see what sort of cache architectures can give us higher performance. If you want to dig deeper into the different memory technologies, I would encourage you guys to use some of these references and follow them. So what you see on the left hand side is a video on YouTube that explains at a fairly high level the role of Intel Optane memory, which is the newer generation non-volatile memory implemented using a technology called phase change memory. It's faster than flash, still slower than DRAM, but it serves a very important role going forward. Here on the bottom you see a web page link, so you may want to look into that as well. So one of the advantages of having a non-volatile memory that is also really fast, like Intel Optane, is it can help us implement very interesting features. Like, for example, if you have a computer and you're worried that your computer can crash because of power failures and other reliability issues, oftentimes when you restart your computer, you have lost the data that the program was working on. And that's a serious issue in many circumstances. So the question is, can we use such non-volatile memory to build recoverable systems, right? So even if the power goes off, can I restart my program as if the power did not go off, right? And so we have done some research on this topic, and if you're interested, I encourage you to read this article. It's written in a way that's accessible to most, but you may still have a few terminologies that you need to get your mind around, but it's still a good read, and I can talk to you more if you're interested. So we, like I said before, our focus at the moment is caches. We said caches are super important because they occupy more than 2/3 of the processor's die area. And we talked about a very simple cache architecture where we had a data array, which is where we store the data, but we also wanted to know the address of the data, so that was stored in a structure called the tag array. For now, we are simplistically assuming that the tag is the entire address. So in this case, I have the address 3 and the corresponding data for that address 3. And we also talked about a bit, which is a valid invalid bit. So when you start your processor, all the bits, all the valid invalid bits would be set to 0, indicating that none of the data is valid. But when you move valid data into the cache line, then the valid bit would be set to 1. So it helps the processor identify which lines have valid data and which ones don't. So I would like you to get familiar with this term cache line. What it really means is this whole row that you see here is what you would refer to as a cache line. So it consists of the data block, the tag that is stored for the data block, and any other metadata that is maintained for that data block to manage it. So that the whole set is called the cache line. Cache block typically just refers to the data that is being stored. Right? So these are two terms that are often used interchangeably, but they do differ in a slight way, and we may see that being used in our course. So please get familiar with these two terms. Okay, so the way that the cache works is fairly simple. You bring in the data, you store along with the address. We said that if you want to look up for a new address, then you would compare that to every element in the tag array using a structure called CAM, content addressable memory, which would tell you which element found a match, and if it did, then you access the data corresponding to that. So if I give an address 5, you will match the address 5 and you can retrieve the data corresponding to that address. And that is called as a cache hit, meaning when I find the address that I'm looking for, that is a cache hit. It's possible that I don't find the address because remember, the cache is a smaller size than the entire address space. I'm only caching a subset of all possible addresses. So it's possible that the address that I want to access, let's say address 10, I check the tag array, the CAM says I don't find the address, so that would be a cache miss. So then we talked about how can I increase the chance that I would find an address, and we talked about this idea called temporal locality that is often present in programs. So basically the idea of temporal locality is that if I access a memory location 1000, let's say, you're more likely to access that same address in the very near future. So to exploit temporal locality, what you would do is if you encounter a miss to any location, you would bring that into the cache and place it in the cache. Now if you have run out of space, you need to find a victim and evict that victim out of the cache and use that victim's cache line to store this new data. And the way that you would select the victim is based on temporal locality, meaning you would want to give preference to data that was recently accessed and keep that in the cache, and evict the one that has not been accessed for the longest time and evict that data. So we talked about a heuristic called least recently used heuristic. So very briefly, here is a simple example. So if I access the address 1, 2, 1, 2, and 3, 2, 3, 2, 3, and let's say if my cache had only 3 cache lines, and now I have a 4th cache line, I don't have space for the 4th cache line. So in this case, 1 is the least recently used cache block, so I would have to evict that cache block. So I didn't talk about how one would implement an LRU policy. There are several ways to do that. We won't go into all possible methods to implement LRU mechanism, but here is a naive method to implement it. So if I had, let's say, a cache with 4 entries, one very simple way to do it would be to have a 2-bit counter per cache line, and that 2-bit counter would tell me what is the LRU rank. So if I have, let's say, I had accessed 4 addresses, 1, 2, 3, 4. Let me make it more interesting. Let's say it's 11, 12, 13, and 14. Right? 11, 12, 13, and 14. So those are my addresses, and imagine that this is my tag array. So I have stored all the tags in my tag array. The LRU rank would say that 14 is the most recently used, so its rank is 1, and 13 is the next most recently used, and 12 is the next most recently used, and 11 would be the least recently used block. So this LRU bits represent the rank of each cache line. And so if I go back and access, let's say, the address 11 again, the way you would update these ranks is by resetting the currently accessed cache block to the highest rank possible, which is 1, and then increment all the other ranks by 1. So I would increment 3 to 4, 2 to 3, and 1 to 2. So now if I have to evict a cache block, let's say I accessed an address 7, I don't have 7 in my cache, I have to pick a victim. I would pick the one with the highest LRU rank, meaning the one with which is least recently used, and evict that and replace it with the new address 7. Of course, I would then have to reset the LRU rank to this to 1 and increment everyone else by 1 to keep it updated. So in this fashion, I can keep track of the lines that are least recently used, and when I have to evict a line, I will know which one to evict. This is a very naive method. There are more efficient methods. If you care about the size of the LRU bits used to implement it, in this example it would be 2 bits per cache line, so that would be 2 times 4, so totally I need 8 bits. For a very large cache, this could become expensive. It's also expensive to update all these counters every time you have a cache miss and you bring in a new block. So there are approximations of an LRU policy. For example, there is a policy called pseudo LRU policy, which is a bit more easier to implement. If you ask the question, what is the least amount of information that I need to maintain to implement a perfect LRU policy, the answer is you need to think about the number of permutations possible for a given number of cache lines, right? So if you think about it, when I specify these ranks, all I need to think about is what are the different permutations possible for these ranks. So the first position, there are 4 possibilities. The second position, there are 3 possibilities, and so on, right? So this is a standard mathematical formulation where there are X number of permutations possible. Like you are given 4 items and you can arrange them in 4 factorial number of ways, and so therefore I need enough bits to express one of those 4 factorial number of ways. So if I need to compute the number of bits required to express 4 factorial, I can take a log to the base 2 of 4 factorial. So 4 factorial would be 4 times 3, that's 12. 12 times 2 is 24. So log to the base 2 of 24, that would be approximately, if I round it off to the nearest integer, it would be 5 bits. So with 5 bits I can implement an LRU policy for a cache with 4 cache lines. The 5 bits is smaller than 8 bits, but it can also be a bit more challenging to maintain the state machine to maneuver through these 5 different 2 to the power of 5 different possibilities. So we also talked about how to reason about performance of caches. So we talked about this metric called AMAT, which stands for average memory access time. So let me work out one more example to explain how AMAT works. So here is an example where I have a cache that takes 10 nanoseconds per access, which is fairly high. Typically it's only a nanosecond if it's an L1 cache. The cache miss takes about 100 nanoseconds, which means the time it takes to go to the main memory is 100 nanoseconds. The question asks you to compute the AMAT if the cache hit rate is 97%. Now the question also asks you to assume that main memory access time does not include the cache access time. So this is different from what we had assumed for the problem that we solved in the previous lecture, and this is one of the common confusion among students when it comes to computing AMAT, because some problems would say memory access time includes cache access time, and some problems say the opposite. So you want to be familiar with both of those assumptions. So for this assumption, when the when the memory access time does not include cache access time, you have to think about the fact that every memory access, a load or a store, would have to first access the cache. And so irrespective of whether it's a cache hit or a miss, I need to spend 10 nanoseconds to access the cache. And then if there is a miss, so the miss rate is 1 minus 0.17, so that will be 0.03. So for 0.03 or 3% of the accessees, I would have to spend 100 nanoseconds, right? So that would be a total of 13 nanoseconds. So my AMAT for this particular configuration is 30 nanoseconds. So we are ignoring disks in this case. Maybe you can assume in your mind that 100% of the accesses to main memory are hits in main memory, so you never go to the disk, even though that's a little bit unrealistic, but we're going to make that assumption for this problem. So now we have given a second configuration. Let's look at this problem here. So it changes the cache architecture a little bit. To try and improve the performance, I'm going to try and increase the cache size. This seems like a reasonable idea. More cache size means that my hit rate would be higher. So instead of 97%, now it's 98%. But the problem with the larger cache size is it's going to take a little bit longer for me to access the cache. So larger the cache size, longer the latency. So it's going to increase by 2 nanoseconds. So instead of 10 nanoseconds, it's going to be 12 nanoseconds. And the cache miss rate is has gone down to 0.02. So my new AMAT is going to be, previously it was 10 nanoseconds per cache access, but now it's 12. Previously it was 0.03, but now the miss rate is 2%, so it's 0.02. The main memory latency does not change, so it's the same as before. So now I have 12 plus 2, that is 14 nanoseconds. So it looks like our idea to improve the performance by increasing the cache size in this example did not work. So this has a higher performance than my second configuration. So this example illustrates the point that larger cache size is not always a good idea. So that is actually one of the reasons why you want your L1 cache size to be fairly small and add level 2 and level 3 caches to try and bridge the space between L1 cache size and main memory, like we talked about a few minutes ago.
This lecture we're going to talk about 4 things. First, we'll talk about cache blocks, and then we're going to talk about another form of locality called spatial locality. We'll work out a few problems, and then we will talk about the differences between a write-through cache and a write-back cache, which matters when you execute stores. So what is a cache block? Well, let's start with the simple cache architecture that we had before. I have a tag array and a data array along with a valid invalid bit on the left. I had made a simplistic assumption that I'm going to store the entire address as part of my tag array, and the data would correspond to the address that is stored in the tag array. So let me assume that my ISA is byte addressable, which means that my data would be of size 8 bytes. Let me also assume that my ISA is 64 bits. So it's a 64-bit byte addressable ISA. So that means my address is of size 64 bits. And because I assumed that my tag is same as my address, my tag is of size 64 bits. Now this is a really high overhead because for every bit of information that I'm able to store, I need to pay a cost that is 8x more in the form of a tag array, which is really high. So now the question is, how can I decrease the overhead of tags? So what I would like to do is to decrease the number of tags I need and hopefully also reduce the size of each tag as well. And there is one idea that is going to be able to allow us to do that. So what I'm showing on the right hand side is a simple memory address space for a 4-bit ISA. It sort of simplifies my example a bit, and it is also byte addressable. So for each I can address each byte of data. So each address corresponds to 1 byte of data, and I have 16 addresses because it is a 4-bit ISA. Now in my conventional simple cache architecture, for each address I would store the data corresponding to it, right? So I'm just caching the first 4 addresses. Like we said before, this is not really an efficient design, because for every 4 bits worth of address, I'm able to store only 8 bits worth of data. This is much better than my previous realistic example, but it's still not efficient. Okay, so now I want to reduce the number of tags, and I want to reduce the tag size as well, like the size of each tag. So let's see how we can achieve these 2 goals. So the idea is to store more information per tag. So what I'm going to do is increase the size of my data that I'm storing per tag from 1 byte to, let me say, 2 bytes. Okay, so now what that means is my tag is going to store the address 0, but that is going to correspond to both address 0 that is stored as before, but also the address 1 is stored along with it. Okay, and I don't need to store address 1 explicitly anymore. So address 2 would store address 2 as well as address 3 along with it. So I don't need to store my address 3 anymore. That goes away. Right? So now you can see that for every tag, I'm able to store twice the amount of information that I was able to store before. Now you will also notice that I don't explicitly store the address 1 and 3, but that's okay, because if I need to access address 1, what I'm going to do is to compute the tag of this address 1. So in a 4-bit ISA, address 1, let me use 4 bits. And I know that my block size is 2 bytes. And therefore, I need 1 bit of information to distinguish between whether it is going to be the first byte in my in my data array, or is it going to be my second byte. So what I'm going to do is, in the given address 1, I'm going to separate that into 2 parts. The first part is, I'm going to call it as a block offset, and the second part is what is going to be a tag. So for the address 1, the tag is 0 and the block offset is 1. Keep in mind that I'm not explicitly storing block offset in the cache. It is an implicit contract between the cache and the processor that an address should be broken down into this tag and block offset, and if I give an address 1, it would be accessed in a way that I would figure out what its tag is, which is 0, and its block offset is 1. And so I will query the tag array with this tag, and I will see that 0 matches with 0, therefore it is a cache hit. And then I would retrieve the corresponding data that is stored in the in the data array, using my block offset. So 0 corresponds to the first byte and 1 corresponds to the second byte. So then I would retrieve the second byte in order to service this address 1. So let's take a look at another example. Let's say we want to access the address 3 instead of 1. So let's do the similar exercise where I break down the address 3, 0, 0, 1, 1, that's 3 in binary format, and I want to break this address into tag and block offset. So block offset, remember, it's log to the base 2 of my block size, which in this case is 2, so it's only 1 bit I need. So I break this into my block offset, short form BO, and tag. So now I need to query for the tag 1 and block offset 1. And I would not be storing 2 as a tag. Instead, the tag for addresses the address 3 and 2, you will notice, is both the same, which is to be expected. So the tag for this would be also 1. So the tag would match with the tag that is stored, and the block offset would then allow me to retrieve the data 130. Okay. So what did I accomplish by doing this? So I increased my block size from 1 byte to 2 bytes, and as a result I managed to store 2 bytes worth of information for every tag. So now my tag is no longer 4 bits, but it is just 3 bits. So for 3 bits I'm able to store 16 bits worth of information. So now the ratio is 3:16, which is much better than what we started off originally. Okay. So I managed to reduce the number of tags, and I managed to reduce the tag size. Okay, now let's go through all of these addresses that we have for this memory that we have, and divide what I'm showing here on this column are the addresses. So I'm going to represent these addresses in binary format and compute the tag and the block offset. So for 0, I'm going to start with 000, 001, 0010. Alright, so I computed, so I represented the addresses in the binary format. And so how do I compute the tag and block offset? Well, we know that the block size is 2 bytes, so log to the base 2 of the block size is going to be 1. So I need 1 bit for the block offset. So I'm going to just divide this whole thing into 2 parts. So that will give me the block offset. So then I can also compute the tag for each of these addresses. So what I see, what is remaining is the tag. So I'm just going to represent in decimal what the tag is: 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. Okay. So you'll notice that the tag for adjacent memory locations is the same, which is expected. Okay. Okay, so here is a better representation of the picture that I just showed you. So we started off with the assumption that each block is of size 1 byte. And so we had a very straightforward case where the address was same as the tag address. So we had to store the entire address as part of each cache line. Not only that, each cache line could only hold 1 byte worth of data. And so the tag size was 4 bits, and the data that I could hold per cache line was 8 bits. So the ratio of useful versus metadata was 1:2. Not great. If you have to also add valid bits and the overhead of LRU bits, which I'm ignoring at this point. But I improved this design by increasing the size of the block to 2 bytes. And when I did that, now I have more information that is stored as part of each cache line. And so now I need only 3 bits for the tag. So for every 3 bits of tag, I'm able to store 16 bits worth of data, which is much better than what I had before, and therefore my area overhead of my cache is much better. So what you see on this column are the tags for block of size 2, and these are the tags for block of size 1, which is same as the address. So the main idea behind block sizes is to increase the data per cache line by increasing the cache block size, which reduces the data that is which increases the data that is stored per tag, and also it reduces the tag size as well. Yeah, let me illustrate how block sizes impact our simple cache design. So again, I have this 4-bit ISA, 4-bit addresses with 16 locations, byte addressable, memory that is shown on the right hand side. And I'm going to execute these toy instructions, 5 load instructions, and their addresses are given within the braces. I have a register file. In this case, I have only 4 registers. And my cache has 2 cache lines, and each tag is of size 3 bits because 1 bit is going to be used for the block offset. The remaining 3 bits of the 4 bits is my tag. Each cache block is going to be of size 2 bytes. Let me execute my first load instruction to address 1. I would bring both bytes that are adjacent into the cache. So address 1, the way I would process that address is to split that into the block offset and the tag. And the tag is what I would store, and the block offset refers to which byte in that block I am trying to access. And remember, we had computed the tags for these two addresses 0 and 1, and we said the tag is the same, so I would be bringing both of those data into the cache. I set the LRU bit to the line that I have not accessed yet, and then I send my data that I just accessed and store it in the register file. So I'm also going to keep track of the misses and hits. So far I just accessed 1 cache block, and that is a miss. Now I access a different address 5. Now if I do the same process, I will break that address 101 into 2 parts. The tag is 2, so that's what I'm going to store here, and I'm going to bring the entire block that corresponds to the address, the tag 2, which is address 4 and 5, into my cache, and I return the value 150, which corresponds to the block offset 1 within this block. I set my LRU bit to the previously accessed cache line. So if I go back and access the same address, the only thing that would change is the LRU bit, and I would get my first hit. Now if I go and access address 4, if I can split address 4 into my 4-bit value 100. If I split that into tag and block offset, I will notice that the tag 2 matches with that of the tag that I have stored here, and then I would use this block offset to get my correct byte. So address 4 corresponds to this byte, and so I would have to write the register 3 with this data 140. So that's what I would do, and then make sure that my LRU is updated accordingly. Now this was also, the previous access was also a hit because 4 was able to find the data in the cache. Now an important property that you want to notice here is that I had never accessed 4 before. This is the first time I'm accessing 4, and it's still a hit. So we will later think about why this happened, and we are going to talk about it as a form of a locality, which I'll define soon. Then if I access 0, again it's going to be a hit. Again, I had not accessed it before. This is the first time I'm accessing it, and because its tag is same as the address 1, and address 1 had brought in both bytes corresponding to that block, I'm able to enjoy a hit even though this address was not previously accessed. Okay, but of course the data that I would return would be defined by the block offset, which is 100. So 100 will be stored in register R2. Okay. So now I said the reason why I enjoyed a hit for the address 4 and address 0 is not because I had accessed it before. If it was the case, then I would say I'm enjoying temporal locality, right? But in this case, 4 and 0 were not accessed before, so therefore the form of locality that I'm exploiting is a bit different. We're going to define a new form of locality called spatial locality. What is spatial locality? It says that if you reference a memory location, let's say 1000, then you're more likely to reference a location that is near it. It's worthwhile to contrast this with temporal locality. So temporal locality said, if I access a location, say address X, I'm more likely to access that address in the near future than a random location. In contrast, spatial locality says, if I access a location X, then there is a very high chance of accessing X plus 1 or X plus 2, X plus 1 or X minus 1. And the chances of accessing X plus 1 or X minus 1 is higher than the chances of accessing X plus 2 and X minus 2. And the chances of accessing X plus 2 and X minus 2 is higher than accessing X plus 3 and X minus 3. So the probability of accessing an address in future depends on how close that address is to a given address X. Okay. Let's consider an example to understand spatial locality better. It turns out that array accesses are one of the common sources of spatial locality. So to understand array accesses, first we need to understand how arrays can be stored in memory. So let's take a very simple 2 by 3 matrix where there are 2 rows and 3 columns. There are a couple of different ways this array can be stored in memory. One is what's called as a row major order. So in this case, I would lay this array as follows. Me as in the compiler would do this. When an array A, which is a 2-dimensional array, I would first store all the elements of a row next to each other. So I would store A11, A12, followed by A13. Now the subscript 1 says this is a row, the next subscript says which is a column. So I store my elements in this fashion, right? So you would notice that the elements in a row are placed close to each other. In the case of a column major order, it's as the name indicates, you place the elements in a column next to each other. So in this example, you do something like this. So A11 followed by the next element in the same column 1, which is A21, and so on and so forth. Now it's very common to use row major order for placing array accesses. And understanding this detail is very important to get performance, because if you know that an array is stored as a row major order, then your program should try to access it in the row major order. And when it doesn't, then it can lead to dramatic performance degradation. So let's take a look at an example how a program would access a 2-dimensional array in a row major order. So here I have 2 for loops that iterate through this array int, and it's iterating through it in a row major order because the first subscript I does not change until I finish accessing all the elements in its column as indicated by subscript j. The way I'm accessing the array is like this, right? I go back, I access the second row, I come back and I access the third row, and I access the nth row, and so on, right? Now let's take a look at an example why this leads to better performance due to spatial locality. So let's say my program accesses the location indicated by the red. Now recollect that when an address is accessed, the whole cache block containing that address will be fetched into the cache, which means, let's say the cache block size is 4 data elements. So all these will be fetched into the cache at the same time after I finish accessing my first data element I0 and J0, which means that when my program wants to access the next data element indicated by blue, I already would have that data element in my cache because I brought it as part of the first memory access. The whole cache block, like I said, was brought into the cache, and that cache block, let's say it had 4 data elements in it, which included the blue element. So in this example, I would incur only 1 cache miss for 4 data elements, and the remaining 3 would be hits. And the reason why those 3 are hits is due to spatial locality. Now if I do not access my array in the same order in which it is stored in memory, then my spatial locality would be very poor, and that can result in severe degradation in performance. So if you go back to the example that we talked about in the first lecture, we did a live demo of it and showed how dramatic the difference in performance can be. And the reason now I think you should be able to understand is due to spatial locality. So the code that performed well was accessing in the row major order, but the code that was not performing well was accessing the 2-dimensional array in column major order. So what happens when I access the array in the column major order? Well, so I would access the first data element that would bring in its adjacent blocks in memory, and adjacency is defined by how the array is laid out in memory. And if you assume the array is laid out in the row major format, then the block would contain, let me say that for simplicity, let me say the block size is 2 data elements, so it would contain x and its neighbor, right? But I'm not going to access its neighbor with this code. The column major access code is going to say, well, the next access is going to be I1 and J0, which is obviously not going to be in the cache, and so I would end up bringing in this cache block, which is of course going to be a miss, and so on and so forth. So if I browse through the array in this fashion, and if the array is large enough, by the time I have gone through the entire row, it's quite possible that my cache is not big enough to hold all the cache blocks that I brought in. So if the cache was not large enough to bring store all the cache blocks that I brought in, it's quite possible that my first cache block has already been evicted due to lack of space. So when I go back to I0J1, that data is not there in my cache anymore. So then I have to bring the whole cache block again, which is of course wasteful, because not only I'll be bringing this data, but I'll also be bringing this data over here, which I'm never going to access in future. So it's wasteful in that sense. So therefore my even though my program has spatial locality, meaning my algorithm has spatial locality, because I'm simply trying to access all the elements in my 2-dimensional array, my given program, because it accesses it in column major order, it does not exploit that spatial locality. As a result, it doesn't have the same performance as the more optimized version. So how to decide on the block size? So if you have too small of a block,
then you wouldn't be able to exploit spatial locality. But if you have a really large block, then it may not be beneficial, especially if your program does not have spatial locality, because then if I access one address, you're going to bring in a lot of adjacent addresses which you may never access in future. So there is a trade-off here where you want to decide on a block size such that it exploits all available spatial locality but does not incur overhead by bringing in data into the cache which never gets accessed in the future. To figure out what is the right block size, one has to take a representative set of applications, profile them, and find out what really works. And that's typically how processor designers go about designing the configuration of these structures. Now we're going to see a few problems based on cache blocks, and for such problems you have to think about how to interpret a given address. So the address consists of the tag and the block offset, and a typical problem would give you the block size as a specification. So from the block size you can compute the block offset size, and that is simply the log to the base 2 of the given block size. You can also work backwards and say, well, if I know the block offset size, then my block size is going to be 2 to the power of that. So now once I figure out what my block offset size is, the number of bits that I would need to specify my block offset, then I can compute my tag size as simply the address size minus the block offset size. And the address size is defined by your ISA. So for a 64-bit ISA it would be 64. For 32-bit ISA it would be 32, and so on. Now let's take a look at a problem, and in this problem we're going to assume that it has 2 cache lines and it has a 2-bit tag field, but it has a 4-byte block. So before in our examples we were assuming a 2-byte block. Now we have increased it to 4 bytes, and as a result the tag size decreased from 3 bits to 2 bits. And the problem asks you to simulate the cache for these load instructions. So the load instructions are given in this direction. So I'm going to first execute this load instruction, and then this, and then this, and this one will be the 4th one, this one will be the 5th one. And I'm going to represent the state of the cache over here. So when I access the address 3, so 3 is 0011, and remember that I have 4 bytes in my block, which means my block offset is log to the base 2 of 4, which is 2. So I need 2 bits in my block offset, which means that my last 2 bits are taken up by the block offset. The remaining is going to be my tag. So when I access address 3, the tag is 0, and I would set it to valid bit and bring the data corresponding to the block containing the address 3, which would be all of this data. So it will be 78, 29, and so on. So then I can carry on this exercise for the next address 12. So if I access the address 12 in binary, it is going to be 1100. So my tag is going to be 3, and that's why I would populate this with 3. And now the previously accessed block is going to be LRU, and now when I access the address 15, the address is 1111. The last 2 bits are block offsets, the first 2 are tag, and I had accessed this block before, and so therefore it is going to be a hit. I don't really need to think more about the data when I'm simulating the cache, though in reality the data is what you're looking for. And
4 address is going to be 0100. The tag is going to be 01. I'm going to be accessing that one. I'm sorry, I would be evicting the address 0. Sorry. So now let's consider the address 4. So when I access address 4, now the tag is 0. I would compare this tag with the address with the tags 0 and 3, and I would discover that it doesn't match, and therefore this is going to be a miss, and I need to find a victim. Because the tag 0 is the least recently used tag, I would evict that out of my cache and replace it with the new tag, which is 01 in its place. And then finally I would access the address 9, which is in binary is this. So then I have a new tag, and so again I would match the tag 2 with 1 and 3 and discover that it's not there, so therefore it is a miss, and I have to find a victim. The victim is going to be the LRU victim, and so 3 would be evicted out and replaced by the tag 2, and that would be my final state of my cache. Okay, so now let's look at another cache problem. So in this case, you are given that the cache size is 8 bytes and block size is 2 bytes, which means that my number of cache lines now let's take a look at another problem. So in this problem we are asked to compute how many bits are there for the tag. So to compute the number of bits for the tag, I need to know what is my address size. So my address size is 16, so the tag size is going to be address size minus the size of your block offset. So the size of your block offset is going to be defined by the block size. So log to the base 2 of 2 bytes is going to be 1, so the tag size is going to be 15 bits. So now you're given an address stream and you're asked to simulate this cache. So again the cache has 8 bytes in it, and each block is of size 2 bytes. So the number of cache lines is going to be 8 bytes, which is the total size of the cache, divided by the block size. So I have 4 cache lines, and I'm going to use my LRU replacement policy to make space when I don't have space for a newly accessed address. So let's simulate this cache. To help simulate this cache, I have a cartoon here. I'm just going to express the tag array because, like I said before, the data doesn't really matter so much when you're thinking about simulating the cache and figuring out whether an access is a hit or a miss, which is my goal. So now what I'm given here is the addresses. So now first step is to convert this into binary so that I can determine what is tag and what is block offset. Okay, I have converted the addresses into binary format, and keep in mind that the block offset was 1 bit, so I wouldn't be needing these because these are block offset, and the remaining would be my tag. So my tag is 0 0 1 2 6 0 1 4 2. Now with these tags I can now go and simulate my cache, and I'm going to use LRU replacement policy. So 0 is not there in the cache, so that is a miss. 0 is there in the cache, that's a hit. 1 is not there, it's going to be a miss. 2 is not there, it's going to be a miss. 6 is not there, it is going to be a miss. So now imagine that I need to also
keep track of the LRU rank. So the LRU rank is 6 is most recently used, and 0 is the least recently used. Now when I access 0, I would have to reset this LRU rank to 1, increment everyone else's rank by 1. This is going to be a hit, and when I access 1, again it's going to be a hit, and I need to update my LRU. So this would become 1, and everything has to be incremented by 1. Now if I access 4, it's not there in my cache, which means that I need to find out who is the least recently used tag. So the rank 4 is the least recently used tag, so I will evict it and replace it with 4. So this is going to be a miss. Now it turns out that I end up accessing exactly the same tag in the next step, but unfortunately I just replaced it, so which means, when I replaced it, I should have updated this LRU rank to 1, and everyone gets incremented. So when I have to replace for 2, I will find out that this is the least recently used, and so therefore the tag 6 will be replaced with 2, and the LRU rank will be updated as well. So the hit rate for this example is 3 hits out of 9 accesses, so that is 33%, which is very low. In reality it's much higher, close to 90% or more. How many bits are needed for storage overhead? So for that you need to compute the overhead as the tag size plus the valid invalid bit and the LRU bit, and we are assuming that we're going to need 2 bits because we have 4 blocks, and so this is a very conservative implementation of LRU policy. And so this is the number of bits you need per cache line. So we have a total of 4 cache lines, so the total overhead for the entire cache would be 4 times 18. Alright, cache problem 2. In this case we are asked to compute the storage overhead for a cache with the following characteristics. So again, the overhead is going to be based on tag, which is the address size, which is 32, minus the block offset, and the block offset is going to be derived from the block size. So if the block size is 64 bytes, then the block offset is going to be logged to the base 2 of 64, which is 6. So that's how you got 6 bits for the block offset. So totally for the tag you have 32 minus 6, and that is 26 bits. And to compute the number of LRU bits needed in the conservative scheme, you need to know the number of blocks that are there in the cache. So that you compute by the total cache size divided by the block size, so that gives you 1k or 1024 blocks, and so log to the base 2 of 1024 is going to be 10 bits. So for every block you need 26 tag bits, which we computed first, and 1 valid invalid bit, 1 dirty bit, and 10 bits for LRU. And totally we need 32 bits times the number of blocks, that you get 38 bits. We have not talked about this dirty bit yet, but we will do that when we talk about the write back caches. So now let's talk about how to handle stores in our caches. So there are 2 policies available. One is write through and the write back that we're going to talk about now. So let's go back to our simple cache architecture where we had cache blocks of size only 1 byte. Again, we have this 4-bit address space with 16 address locations, and each one refers to 1 byte of data.
So now let me assume that I had accessed addresses 0, 1, 2, and 3. So that has populated the different locations in the tag array, and the data corresponding to those addresses have also been loaded in the respective cache lines. Now let's say after these memory accesses, I get a store, and that store is to a location 0, and I want to write a new value, let's say 50, to that location. Now the question is, do I overwrite only the cache data, which sounds like I need to do, or do I also update the value for the address location 0 in memory to the latest value? And if the answer is yes, for every write, I am going to write through the latest value to memory. It's called as a write through cache. So in the case of a write through cache, on a write, I'm not only going to update the value in my cache, but I'm going to write it through to memory. Now let's say I executed a few more of these stores and I wrote different values to this location. Now each time I would have to do the same thing, which is update my cache, update my memory, update my cache, and update my memory. Now as you can notice, we are frequently updating the memory. In other words, we are not really exploiting the temporal locality for between these stores to the location 0. As a result, we have too many writes to memory, which can be inefficient. We know that main memory is slow, but it is also true that the bandwidth to the main memory is also limited. So bandwidth is different from latency. Latency means how long does it take for me to get a data item or write to a data item. Bandwidth means how many reads or how many stores can I perform in a given period of time. Now if I'm going to do so many writes, then I'm going to consume a lot more bandwidth. And so now you may be wondering, is there a way in which we can avoid these write-throughs? And the answer is yes. So let's say that instead of writing through to memory on every store, I am going to simply update my local cache with the new value 50, and I'm not going to write through to memory, which means that the value in memory is now going to be stale with respect to this new value 50, and I'm going to be okay with that. So when I have the second store with value 51, I'm simply again going to update my cache, and then if I have value 52, again I'm just going to update my cache, and this value in memory is going to be this old value 74. Now the question is, at what point do I update the memory with the correct value? Well, at some point I may run out of space in my cache and I may need to evict a data block. So let's say in this example, 0 happens to be the most recently used, so if I were to access a new address, it's not going to get evicted. So let me assume that after these accesses, I'm going to access, let's say 1, 2, 3, which would make 0 the least recently used address. So now let me go and access a new address 4, which would evict this cache line. Now this cache line has a new data for the address 0, and that needs to be written back, right back to memory. So when a cache line gets evicted from
the cache, that is when the latest value gets updated to memory. And so now this line would be allocated to 4, and 4's value is 140. Okay, so the principle of write back cache is that I'm going to allow stores to modify only the data in the cache, and only when that data is evicted later on it would be returned back to the memory. Now the question is, let's say I accessed location 5, which is going to evict the least recently used block 1, and now the question is, do I write back the value 110 to the memory? And the answer is no, I don't have to, because I haven't really modified it. And if I have not modified it, the value will be same as what it is in memory, so I can just throw this data out and nothing would change. But the question is, how do I know whether a cache block was modified while it was sitting in the cache? Well, I don't know that, right? So I don't know the difference between a data block that was modified and a data block that was not modified. And in order to get that information, I'm going to have an additional metadata. I'm going to call this as a dirty bit. So the functionality of the dirty bit is that it's going to tell me when I'm evicting a cache line whether that cache line has been modified or not. And if it was modified, then I know that I need to write back. If it was not modified, then I don't have to write back. So when I bring in a new cache block, I'm going to set these dirty bits to 0. And when I have a store, let's say in this example, I have this address 5, that's 150. So let's say I happen to write to this address. Let's say the value is going to be 77. So I'm going to write this value to 77 because it's a write back cache. I'm not going to update the memory yet, but I'm going to note down the fact that this was actually modified. So later on, when this cache line gets evicted, I would check this dirty bit, and if this bit is set, then I would have to write back. The second decision that I need to make is whether to allocate a cache line when I execute a store to a cache block that is not there in the cache. So when I do allocate a cache block, it's called as a allocate on write policy. But if I choose not to allocate a cache block for a store that misses the cache, that is called no write allocate policy. And in some systems, they observe that writes don't necessarily mean that I'm going to be using the data in the near future, and so they may choose to go with the no write allocate policy. But like we talked about with the temporal locality, dictates that if I access a location now, I'm more likely to access it in the near future. And if that applies to writes, then you would go with allocate on write policy. If you think that temporal locality does not apply to write, then you would go with no write allocate policy. So let's go through a few examples to understand the difference between write through cache and a write back cache. So first we will look at write through cache. So here is an example where now the cache block size is 2 bytes. And I have several load instructions and store instructions which I'm going to simulate. So my first address is 1. I bring the cache block corresponding to the address 1. I bring the block corresponding to address 7, whose tag happens to be 3. And then now I'm going to modify the address 0. So address 0's tag is going to be 0 and the block offset is 0, which means that this is the byte that is going to be modified. So because I'm simulating a write-through cache, I need to write the new value, which is the value R2, which is 173. So I have to write back that value to memory and also update my local cache. Now I have a new address 101. The block offset is 1, tag is 2. Now this is not present in my cache, so this would be a store miss. I'm going to follow a write allocate policy, so I'm going to bring in that data into the cache corresponding to the block address 5. And then I have my write through policy dictating that I need to write the data that I just updated. Let's say that is 29 because I'm writing R1 to memory. So now that new value has to be written back. So I have to read the block corresponding to 5, store it in cache, and then write the new value to my cache and then to my main memory in the case of a write-through cache. So carrying on with this example, I have a load, and then the load would simply go and read the data and replace the data. So notice that in this case I do not have to do any action when I evict this block with the tag address 0, because in the case of a write-through cache there is nothing to write back because you have been writing through on every store. So in this example, the number of reads from memory is 8 bytes because we brought in 4 blocks worth of data for 4 misses. And the total number of writes to memory is only 2 bytes. So we wrote 1 byte per store. Each store is writing to 1 byte of data, so therefore when I wrote to the memory, I have to write 1 byte per store. So totally we had 2 stores, and so therefore I need to write 2 bytes of data to the memory. Now this might give you an impression that, well, I didn't really write a lot of data to memory, and so looks like write-through caches is not such a bad idea. But keep in mind that typically the cache misses are fairly low, which means that the amount of data that you would bring in from the main memory would be much less than the number of writes that you would be executing in your program. So in a practical system, the total writes to main memory in the case of a write-through cache would be enormous. So the write-through cache would consume a lot of bandwidth. But the advantage that you have with the write-through cache is that the cache and the memory stay consistent all the time, and that has some benefits, especially when you have multi-processor systems, which is not something that we're going to talk about in this class. Now let's take a look at how write-back caches would work for the same example. I have now added a D bit, which stands for the dirty bit, which is the one that is going to help me keep track of whether a cache line has been modified or not. Now I'm going to simulate for the same sequence of instructions. Address 1, fetch the block. Address 7, fetch the block. Address 0, I'm going to write to the address 0, which means that R2, which is the value 173, has to be written definitely to the cache. So this value has to be modified, and I need to set the dirty bit to 1, and notice that I don't have to write this to the memory yet because this is a write back cache. And I carry on from here. I have to store to an address 5. Um, address 5 happens to be a new block, so if you remember, the tag is 2, which was not there, so I brought the block in, and then I have to write the value R1, which is 29, and I updated it, and after I updated it I set my dirty bit as well. So now both cache lines have been modified ever since they were read from memory. Now if I'm going to access a new cache block, so 10 would be 1010, so that will be tag 5, which is not there in the cache, so it's a cache miss. I go and fetch that block, and then I decide that because this cache line is the LRU, I'm going to evict it, and I check my dirty bit, it's set to 1, which means that I need to write back my content to the memory. So now in this case, I don't know which of these 2 bytes were modified. When we executed this program, we only modified the first byte. We did not modify the second byte. And you will notice this from the picture that the first byte is not consistent with the memory. The second one is indeed consistent with the memory. But in the case of a write back cache, the dirty bit is being maintained for the whole cache block. So you wouldn't know which part of the cache block needs to be written back. So conservatively, you have to write back the entire cache block to the memory. And that's exactly what you do in this example. So writing back 29 is just wasted work. It doesn't affect correctness. And then I bring back the new cache block and everything is done. So in this example, the number of reads from memory is still the same because the number of misses did not change. So whether you choose to do write back cache or write through cache, it does not change the number of cache hits or misses. What it changes is the number of writes to memory. Typically in the case of a write through cache, you would have more writes to memory, but in this example it turns out that we ended up having more writes to memory even in the write back cache. Why is that? Well, remember I said that when you write back a cache block, you have to write the entire cache block, and we wrote back 2 cache blocks, and each cache block was of size 2 bytes, and so therefore we had to write back 4 bytes. So even though I had to only write 2 stores, in the case of a write through cache, I had to write only 2 bytes worth of information. In this example, in the case of a write back cache, I had to end up writing 4 bytes. But this is a contrived example. In a realistic system, a typical program would exhibit quite a bit of temporal locality even for stores, and so you would be able to save significant number of writes to memory by avoiding them being written back. So they would, when I write to the same address over and over again, they would all go to the cache, and then only when I evict that block later on, I need to write once. So as a result, I avoid writing 1, 2, 3, 4 times, and instead just write once in this example. But for the example that we just went through, I would have to choose write through, just because it would have had fewer writes. To summarize, we talked about a simple cache design, where the main question you should be asking is, what is my cache size? And then today we talked about block sizes, which determined how many cache lines I would have, which can be derived from cache size and cache block size using the simple division operation. And then when you're designing a cache, it is also important to specify what type of a replacement policy you want to use, and that depends on what type of temporal locality your programs are likely to exhibit. We talked about LRU policy at length. It's least recently used, but there are also other policies that people have talked about, but they have found out in practice that they are not as effective as LRU. So some examples would be least frequently used cache block, meaning the cache block that I have not accessed as frequently as the others. The other option is FIFO, meaning first in, first out. The block that you would evict would be the block that got into the cache first. And the other policy is random, just randomly pick up cache block to evict. So none of these policies work very well in practice, but of course you can always define a program for which these would outperform LRU. So we also talked about how to reason about cache performance. One very important statistic about a cache is its cache hit rate, and that can change from one program to another program, even for the same cache. And then we also talked a lot about the latency of a cache, and using this information we can compute a performance metric called AMAT, which stands for average memory access time. We also talked about the area overhead, which is defined by all the metadata that we have to store for every cache line, including tags, valid bit, dirty bit, which is what we use for write back caches, and then bits for implementing the LRU policy.